Okay, so my name is Romain Yvinec. I'm really happy to be here. I stay about 2 months. Nice program. And here are some of my collaborators on this subject, so they are a bit spread around the world, in France, USA, Brazil. And I will actually start to work on the board. So just to give you a rough idea of what it is before going to the math, I'm working on coagulation-fragmentation models, very specific ones, I will detail. And this is applied to protein aggregation involved in many amyloid disease, like prion disease, Creutzfeldt-Jacobs, and others kind of disease. So, but my main objective of this talk is, for me, is that you understand the models. I wanted to spend a bit of time writing the equation and the kinetic models. So, it's a particular type of model called Baker drawing. You guys are physicists. I'm a physicist, I think. 35.
So wait, before you start with this, why don't you explain the connection with the biology?
Yes, this will come.
This will come.
It's actually the first slide, but before that, I really want to write down the equation. It's easier than to speak, for me, to speak with the connection with the biology. So this model is a coagulation-fragmentation model that could be summed up with the kinetic chemical reactions that I'm sure you are familiar with. But it's a very particular kind. So Ci here is a C, and this is I, is a cluster of I molecules. Okay? And C1 is very special. C1 is a cluster of one molecule, so I will call it a monomer. C1 is a monomer. And then this cluster may evolve in time by increasing their size or decreasing their size, okay, one by one. So in coagulation fragmentation model, usually you can put several clusters together, I plus G is I plus G, right? Here it's only 1 plus I, okay? And we put some reaction rates, P and Q that may be size dependent, okay? So the typical application for the dependence in size is polynomial or rational function of I to the power 1/3 when you take into account the space and so on. So in my case, I'm actually working with non-spatial model. Okay, well mixed. And I'm working with a mass action law. So you also think of different stuff, but here would be only mass actions. And then you have, when you have specified this, you have two choices. It could be deterministic or stochastic, right? And I'm going to detail a bit the equation in both cases. So, for the deterministic theory, we'll write up a set of ordinary differential equations for each cluster of specific size. Okay? Yeah.
And you making the assumption that a longer chain can't break up into two longer chains,
indeed,
and that two longer chains can't connect as well?
Two long chains cannot connect, and a long chain cannot break in two long chains.
And is that realistic?
To my point of view, for the biological problem I'm interested in, yes, to a certain extent, of course. You could think of different schema. So these are real steps involved in the nucleation part, and in the beginning of the process, it seems to be realistic. So if you write down the mass action for this guy, so I equal 1 is a bit special, but for any other guys, this will be written like this, just mass action kinetics, which has a very specific form, of course. So each guy for I bigger than 2 is involved in 4 reactions, okay? 2 reactions here, and with this circuit change, 2 reactions also here, right? So with this you could rewrite as the difference between 2 flux, right? Gi minus 1 minus Ji, okay? Where I will define this G minus 1. I'm calling about a flux. Okay? So these 2 terms are the exchange between the I minus 1 and I cluster. And these 2 terms are the exchange between the I and I plus 1. which you can then define as a flux. Okay, and for C1, it's a bit different. So for C1, because it's involved in all of this reaction here, you will get a term like this. So any of the flux affects the evolution of the concentration of the monomer, and the balance is with a minus negative, because I call it the flux here positive. So it's minus of all the flux, and for the first one, because it's 2C1, you get C1 plus C1, you get a 2 here, which is a little bit different. Okay, there is something very important in this particular model, which also is the case in more general coagulation-fragmentation, is the mass conservation. So at least formally, you see that any reactions preserve mass. So the mass here is 1, the mass here is I, and the right-hand side is I plus 1. So when you sum the mass, it's preserved, right? It's not that trivial in the set of ODEs, because it's an infinite set of ODEs. But you can actually show that the mass is indeed preserved. So if I use a typical initial condition of this type, I will be interested in all the mass being concentrated in the monomer, so I call it a pure monomeric initial condition. So if all the mass is present in the monomer form, so this is like a Kronecker symbol, right? Okay. Then I will have through time this conservation. Okay, so you can see as a summing, try to differentiate this infinite sum, and all term will cancel. Okay, but when you do this, you take the differentiation of an infinite sum, so it's not that easy that it works, but it is indeed the case. There is another way to write down this equation. I'm going to use it later. It's called the weak form. So if you take a sequence of test functions, if they are appropriate, so I'm not going to the detail, but you can calculate this quantity. So you multiply each equation by phi I, then you sum over all the I, and you will get actually the adjoint of this set of equations. So if it's slightly easier to see down this form, you multiply everything by phi I, and then you do an inversion of index, and it will be the sum of phi I plus 1 minus phi I plus gi. Okay? So you multiply everything by phi I, and then you sum over all the I. This I minus 1 minus gi times phi I, you can rewrite as phi I plus 1 minus phi I times gi. Okay? And then you have to remind about the last one, and the last one will give you minus phi 1. Okay? For all reactions, you lose a monomer or you win a monomer, or you win a monomer. Okay? So here in this form, you can see it as what's happened in every reaction involved in the flux I. You lose a cluster of size I, you lose a monomer, and you win a cluster of size I plus 1. It's a different way of writing the equation. Okay, and in particular, if I do only the sum starting from 2, what I get is 2. And I get this. So I'm forgetting about the phi 1, okay, here, but then I have a rest because this sum doesn't cancel each other. So I still have this G1. It's like the boundary flux. Okay. So that's the deterministic part. So before going to the stochastic model, which I'm really studying, I want to detail a little bit of classical analysis for the deterministic model. We can do this. So as I said, it's not easy actually to do this mass conservation. So to prove this mass conservation, you have to sum an infinite set of ODEs. okay? And it's not so easy that it will work. And one sufficient condition, sorry, is that the size dependent of, how do I call it, pi, or the aggregation rate, is not bigger than I when I goes to infinity. Okay, so if you impose that the growth rate is sublinear with the size of the cluster, then you ensure that your model is well posed. And actually there are counter-examples. So for instance, if you take I square, okay, for the aggregation rate, then you can prove actually that you have a blow-up in any positive time. So the solution is not defined for any positive time. So this is really you need that in deterministic theory. What's happened if it's I square, for instance, it's more or less like what's happened in x1 equal x squared, roughly, okay? But this happens in any positive time. So you have a blow up as soon as t is positive. And then there is, so the most interesting part is for the steady state analysis, so the long-term behavior. And this is where this model has been used for. So if you try to compute the steady state, at least the candidate, you have to set the flux equal to, the difference between the flux equal to 0. So all flux has to be equal, okay? d over dt of ci equals 0. And because of the first equation of the monomer, all the flux being equal, they have also to be equal to 0, right? For d over dt of c1 to be 0, okay? So the stationary state must satisfy gi equals 0 for all I. And this you can reformulate as ci, so writing explicitly, pi c1 equals qi plus 1 ci plus 1. Okay, so you have a set of equations like this for all I, which you can solve. So it's just a recurrence equation, right? And you get a power of the monomer, okay, where qi is simply the product. I don't know if you can all see here. You tell me if not. You get a recurrence like this, okay? So the particular form is not so important, okay? You get power law. So Ci is the power of C1 times the prefactor, right? C1 is not determined, and you hope to determine C1 by the mass conservation. Okay, that's one freedom you have in addition. So you hope to find C1 with the sum of ICI equal M, which you can rewrite as the sum of I QI C1 times I equal M. Okay? So in principle, you are done, because this is a smooth function, so the sum is infinite. Okay? So this is a smooth function of C1, and it should go to infinity when C1 goes to infinity. So you should eventually cross this level M. But things are not so easy. So if you look at specific example for f, for this function, so it's an infinite sum, and actually what can happen, it has a radius of convergence, right? So this sum may blow up for a large z, okay? So it's like a series, and it's with integer power, right? And typically it has a radius of convergence below which it's finite and over which it's infinite. But you're not guaranteed that it goes smoothly from finite values to infinite values. Okay, so there are examples where this function is doing something like this, and then it's infinite. Then this function do not take all values between 0 and plus infinity. So if your mass is below this critical mass, you're safe. You will find a solution to this. But if your mass is above, there's no solution. So what actually happens is if your mass is above this threshold, you do preserve mass for all time. Okay, this is a theorem, it's not guaranteed, but you can actually prove it. So you do preserve the mass for all times, but not at stationary state. So typical result read like this. So it's really a nice theorem because it uses actually not so, sorry, missed the name. not so involved fancy theorem. It's just like duality and Lyapunov theory actually, because this system has a Lyapunov function. This was based by 86, which states that there is a critical mass, okay, such that if m is below this critical mass, C of t, so I'm writing C of t the all of the Ci, right? Just short notation. So C of t will converge nicely to a stationary state in strong norm. So everything is fine. In this stationary state, you will find it solving this equation. But if the mass is above this critical threshold, so in particular, if the critical threshold is infinite, so which can occur for specific coefficients. So if the mass is above, then C of t will only converge in weak norm toward states which has a lower density, which has a lower mass, which has a mass equal to the critical mass, but not the initial one. Okay, and C of ms is of mass ms strictly lower than m. Okay, so this is really a classical result in this field, which is used as a phase transition phenomena. So roughly what's occurred here, you have a loss of mass in infinite time, and this loss of mass is going to a different phase. Okay? So as long as your mass is constant, it's still the same phase. But as soon as you have some loss of mass in your model, you say it's going to a different phase, right? Transition phase. And this transition phase occurs for this model in infinite time. For other models, more generalized coagulation-fragmentation model, it could happen actually in infinite time, right? But here it's only in infinite time. Okay, so this, although it's not strictly related to my work, it's really important and to realize what this model are used for. So it's really to explain how you can lose mass in infinite time, although you never lose mass in finite time.
And what do we know about the asymptotics? About CT converging to the solution if you do CT minus this, how it goes to...
This is the speed of convergence.
Yes.
Yes, there have been recent work. I think in both cases actually, people are only able to prove algebraic convergence, but not exponential one. But it's not clear whether there's no exponential convergence or not. Okay. So I think it's still open.
Is this case two what's called gelation, or is that something else?
Yeah, indeed, it's what's called gelation. However, people call gelation when it's occurring in finite time. So it's, yeah, well, I mean, you can call it gelation anyway. This is exactly the same phenomena in small soft key or more complex coagulation-fragmentation model, where you lose some mass, but in finite time. Here you lose in finite time. Actually, it's occurring in finite time because you have imposed some condition on the growth of the coefficient. But if you take I as the power 1 plus something, it's occur actually in 0 time. So in the Vector-Domain model, it's either 0 or infinite. So there's no between. Okay, so now I'm going to talk about the stochastic model. And it's easy to write down in the same form, perhaps using Poisson processes, using stochastic equation. So I had the flux, I had the evolution through time of the concentration of a cluster being the difference between two flux. It will be the same here. So there are some initial conditions. Plus the flux at I minus 1, minus the flux at I. But now my flux are defined through Poisson processes. This is the aggregation, and this will be the fragmentation. Okay, so it has exactly the same form. Well, I just erased it, but it has exactly the same form. The evolution of cluster I is the difference of two flux, but the flux are written in integral form. and they are written thanks to Poisson processes. So I1 yi plus yi minus are standard Poisson processes. So maybe some people are more actually familiar with the chemical master equation, and you can actually write down what's the chemical master equation for this model. You need a bit of notation because the state space is a bit complicated. So what would be the state space for this model? You are going not, because you do unit jump with Poisson processes, you are staying in the integral lattice, but if you start at the integral lattice. Okay. So the state space will just be all the configuration Ci, which are integer and which satisfy a mass conservation. Okay. So my small m has become a capital M because now it's an integer, and you can actually see that because it's an integer, now the sum is actually finite. So actually the well-posed theory in this type of system is just trivial, because the number of configurations that satisfies this, being integer, is just finite. It could be potentially super large, but it's finite. So it's just a Markov chain in a finite state space. So you are completely free to choose whatever you want as a coefficient from the reaction rate and so on. The system just exists, it's unique, and for all time. If you are willing to write down the Fokker-Planck equation, or the chemical mass equation, if you write the unique vector where the 1 is at the I position here, okay, with the stoichiometry of each reaction, just losing one monomer, losing one aggregate of size I, and gaining one aggregate of size I plus 1, or minus this vector, okay? And then the Fokker-Planck, the master equation, would look something like this. You will need a sum. This will occur at speed, I should put it maybe before. Number I, C, so this is the probability to step in the configuration C, and the probability to step away on the I, P, Q, or C, where my lambda I are exactly these guys. Okay. So this should be a plus here, and this is a minus, and the I minus, and I will get exactly the same sum, but for the propagation rate, I have to take care that I'm going to the other direction. So as you can see, the equations are a bit long, so you don't really want to work with it, or at least I don't want to work with it. Maybe you can do some stuff with that. It's even hard to exactly quantify how many configurations there are like this. I think it's really a hard combinatorial problem to say how many configurations there is that satisfy this. So if m equal 2, 3, you can do it. But if m is just 10 to the 10, not so easy. So then this will be unfinite sum, of course, but they are actually huge. Okay. What I want to do with this now is just to show you that actually the form of this equation are really similar. So this is the forward equation, and you can work with the backward if you like, or actually it's the generator. So if I write the generator of my stochastic process Ct, right, which is the configuration C1, Cm, and T, right, I could write the generator, and it will have exactly the adjoint form of this, and it will actually have the same form as this one also, as the weak form of the ODE. Right? So I can do this. It will be a sum. And now where am I going? I'm going from C plus mu I at the speed lambda I plus. And I'm going at C minus mu I at the speed lambda I minus. Okay. So you have to take care of the labeling. The sum probably start at 1. Yeah, I mean, it's possible sometimes I make mistake about what's the beginning of the start of the sun, because you have some shifting index. But anyway, that's how it looks the equation, right? And if we take a specific test function, so these are also called test function, as in the weak form for the ODEs. So if you take f of c to be the sum of ci phi I, so that function depends of an auxiliary function phi, okay? What's happened for this? Fc plus mu I minus f of c, it's exactly phi I plus 1 minus phi I minus phi 1. Okay? And this was exactly what was occurring here in the weak form of the ODE. So indeed, both processes are really the same. But where's the crucial difference? If we want to compute the mean of the number of clusters of size I, okay, so you could do that taking f of c equal phi of I equal 1 at IM position and 0 elsewhere, okay, and use this set of equation and directly obtain P1 minus 1, the expectation of C1, C1 minus 1, so now you will get a set of equation, a finite set of equation. I goes to 2 to n. So the equation for I equal 1 again is a bit different, but you can figure out, I guess. And the crucial difference is that in the expectation you have a product, and you cannot sort out this as a product of expectation. Right? You have some correlation between the number of the clusters, so you cannot get rid of this correlation, and you cannot close this equation. So it's infinite. If you want to write down this equation for this, then you could involve a third moment and so on and so forth. Okay. But you could still use some closure moments, of course, to get an approximation. Okay, so what you do in practice usually when you have this set of equation, you can try to solve this, but for very small m, or at least I know how to solve this for very small one, but not for large. And if not, you can simulate this set of equation using Gillespie code. So that's down to what I'm doing in practice. So in practice, in the biological problem, I have n equal 10 to the 10, or even 10 to the 15. So if I want to try to simulate this with initial condition 10 to the 10 or 10 to the 15, I think I will get some problem. Actually, I never tried. Maybe there are some fancy ways to do, but I don't know how to do. So I actually work with some reduced model, right? And this reduced model looks like this. So I'm going to switch back to the deterministic form because it's slightly easy, but I can do the same reduction on the deterministic, on the stochastic one. So I remember you had on the weak form this set of equations. Plus some boundary terms. And now the sum morally goes from 2 to 10 to the 10. Okay? So it's quite large. And the trick is to take epsilon equal 1 over something big. So that's 10 to the 10. So it goes to 0. Okay? And instead of focusing on each size, discrete size, we're going to use an approximated function. But we put all discrete size into something that looks more continuous. People call this coarse graining. Okay. So what's this look like in the picture? You have size 2, 3, 4, 5. You put everything close together, and you have the step functions like this, exactly this. Step to 2. And at some point, if you let epsilon going to 0, you hope that this step function will be smooth, right? For the steps, epsilon goes to 0, so the difference between all of them will be small, and you hope this will be smooth. So using this set of equations, you can derive an equation for this, which is not too hard to see. Actually, you have the difference I plus 1 minus I, which become I plus 1 times epsilon minus I times epsilon, which looks like a phi prime, right? If you normalize things correctly. So upon some normalization, but I'm not going into detail, you can actually prove that d over dt over the integral of f epsilon against the test functions. Look at the limit, epsilon goes to 0. So phi prime of x, g of tx, plus my boundary term, which looks like this. So of course I'm skipping a lot of details, but roughly the idea is exactly like this. You have introduced a step function of size epsilon. This difference is going to give you phi prime. Okay, roughly it is phi of I plus 1 epsilon minus phi of epsilon, which you know you do a Taylor approximation, and this is it. Right. So if you had normalized the time by epsilon, this one goes away, and you end up with this. Okay, and this flux, the limiting flux, is something that looks like this times your functions. Okay, so in the beginning you had pi c1 ci. Here you have p of x c1 f of x. Okay, and you had in the reverse minus qi ci, and you have here minus qf. Okay.
You still have this j sub 1 out of this
Yeah.
discrete component.
Yeah. So you still have this discrete component, and it's actually where my work is. So it's involved a bit of details, but the idea. So you have this equation at the end. So d over dt integral of f phi equals phi prime p of x c1 minus qx f dx plus this boundary term. Right. This is a weak form of a transport equation, which looks like this: df over dt plus inverse psi x c1 minus qx f of x equals 0. Okay, so if you multiply this by 5 and do the integration by part, you exactly recover this part. Right? And this transport equation is well defined using the characteristic method only if the flux is negative at 0. Right? So if the flux is positive at 0, this is ill-posed because you require a boundary condition.
So just the equation itself.
The equation itself is not enough to
So sorry, I'm asking something much simpler. If you just wrote down a large volume mean field equation for this, then that's the transport operator corresponding to that, right?
Yeah, definitely. And here is exactly where is your boundary condition. So the boundary condition would look like at 0, you have to equal the flux coming from the transport and coming from what's here in the right hand side of the weak form. Okay. So the specific form of this boundary condition depends on some details of how you scale the weight and so on. So that's why I'm not going to show you all the details. But if you really want to see, I will be happy to give you. Switches here.
Sorry, but I guess what I'm confused by is it almost looks like you've gone back to a deterministic style.
Yeah, indeed. So in both cases, actually, so I started from this here from the deterministic one. Right? But in both cases, you see, I'm doing really like a large number limits. So that does not really matter whether I start from the deterministic or the stochastic one. So our method of proof here, it's kind of easier to write down in the deterministic sense. What you will get in stochastic equation, you get a martingale. You get the generator plus a martingale. And the martingale actually goes to 0. Yeah. Right, when epsilon goes to 0. But that's where the important things are. So it's about the martingale. Okay, so some biology for you. So I'm interested in the dynamics of amyloid. So So, few reminding on what's amyloid disease, at least some amyloid disease, because there are really a lot of them. One famous is a prion disease. So it's the prion is a protein involved in the MATCO disease or the Creutzfeldt-Jakob disease. This protein, PRPC, you all have in your body, in your neuron cell actually, or at least in the neuron cell, maybe elsewhere. And if you don't have luck, this protein can misfold, but in very rare event actually. But it's very rare that this protein will misfold. Or it will misfold but won't stay a sufficient amount of time in this form and will switch back to the normal form. Okay, and this misfolding protein is called PRPSC, which comes for scrappy, which is another type of prion disease. So this protein can misfold, okay, that's it. And when it's misfold, it can eventually, so this is the misfolding protein, the square, the red square, it can eventually start to aggregate with some other misfolding protein. And nothing really happens until it reaches a critical size, called the nucleus size, upon which it will fastly aggregate. So this is really like the Prusiner model, we got a Nobel Prize for this, 1995. And if it has reached here, roughly 6, I think, in the picture, this critical size, then it will really quickly polymerize, meaning aggregate more and more square protein, and long time enough, short time enough actually, but when these guys become really big, really big, it will start to break down, as you were mentioning in the beginning. So this large aggregate eventually breaks down and puts more nucleus or size larger than the nucleus in the system, that will aggregate and aggregate. Right? So you have some autocatalytic process. With a really low barrier here, so this event is really low in time, very slow, whereas here the steps is really fast. Okay. So this kind of model, it's called nucleation-polymerization, is very popular because it explains many things. It explains sporadic appearance of the disease. So sporadic means we don't really know the cause, of course, which can occur for anyone because bad luck. Okay, you had a really rare event occur in your body. But it's also explaining the infectious part of the disease. So, you know, the MATCO was really infectious. If someone you get infected by a seed, what you call a seed, so a preformed large aggregate of prion, then you will overcome this barrier and go directly to these steps and produce a lot of amyloid very fastly. Okay? And here was for the explanation why monomer addition. So actually people have looked really at detailed kinetics of how things occur in vitro. And at least it's plausible that it occurs only monomer by monomer. Of course, it's not like the end of the story. So this is really what's happening in vivo. And what people are able to do actually is to take this protein to use a recombinant form. So it's not clear if the recombinant form is exactly this one or a different one. But they kind of get rid of this barrier, so they can have a protein that have a tendency to aggregate a bit faster than in vivo, right? To perform in vitro experiments. And you can get this kind of data. So here what you observe is the mass of polymer. So it's really like the sum of ICI. I starting from something but bigger than 1. Okay, we don't really know up to which size you can observe the polymer. So it's not exactly the mass you observe, it's a fluorescence, which fluorescence is linked to it's proportionally linked to the mass. Okay. So you start with the pure monomer, so no mass is formed. And through time, you will observe that the mass of polymer increase. And you do this for different concentrations. So I'm taking this picture from Zula, which actually in Leeds. Some of you know that this lab. And this one is not for prion proteins, for different proteins, but it was the same. At least in the kinetics. So in low concentration, low meaning 10 to the 12 number of guys, but it's a low concentration in here, and here it will be 10 to the 14. In low concentration, you have these blue curves, and you have, I think you can agree, it's a kind of all looks the same, but time shifted. So meaning that the slope here, you can measure the slope, won't vary between one curve to another curve, at least among the blue ones. Okay, but the time at which it starts, which is defined by this lag time, okay, it's starts roughly here, the threshold. The time at which the reaction starts is really highly variable from one replicate to another replicate. Okay. And when you increase the number of proteins, or you increase the concentration, you get rid a bit of the lag time, so it's shorter, but they all look translated from each other. And actually, if you quantify the variability of the lag time, so the standard deviation scales linearly with the mean, which argue for exponential law. Okay, so the CV is 1. Standard deviation divided by the mean is 1, or constant. And so even if it looks less variable, it's just because the scale has been changed. Okay, and the kinetics, the statistics, roughly still look the same. So the standard deviation is still equal to the mean for the yellow, for the red, well, for the blue. I'm not really working on this data. I'm working on a different set of data, which is for the prime protein. They look a bit less nice. So I just want to say you how exactly this data is done. So actually what you see is some measure. So each symbol is a time measure. And when you first do is try to smooth a bit the curve by a fit, like a nonlinear curve fit, like a sigmoid or stuff like this. You do a fit, and with this fit, you try to estimate some of the parameter, and I'm really interested in the lag time, so the time at which the reaction starts. You don't really see the event at which the reaction starts, but you see an increase, you fit with a nonlinear curve, and then you put some threshold somewhere, and you have a rough idea of what was the time at which the reaction starts. Okay. Yeah, this is how to explain with three curve. So you have actually this three curve. You first normalize the maximal value, so the data I showed before was normalized by the maximum. And then when you really, what I'm really interested in is the time shift. So I put all this curve together and I record the shift. Okay. But then I'm not interested anymore in what's happened after. Some people do. What you can do is that so for each curve you measure the slack time and you do some statistics, how it depends with the initial conditions. In log scale, so in classical nucleation experiment, in classical nucleation theory, when you do this kind of plot, so you plot the log of the lag time versus the log of the concentration. You should have a linear curve, so you see here it's not clearly a linear relationship, but you can still fit with the curve. And the slope should be equal to the size of the nucleus. So unfortunately for my case, I think it was should be equal to minus the size of the nucleus. So in my case, I think it's 0.5, the slope, minus 0.5. So it would be like the size of 0.5, which is not really nice. Okay. So this kind of, I'm showing this just to tell you that this kind of kinetics are not obeying classical nucleation theory. Okay, just a reminder, this is so the model, which is exactly the same here. So we are trying to explain the variability of the nucleation time through this set of equations, through a stochastic version of the Becker-Doring model. And even though there's no space, the picture looks like this. We start with monomers. These guys tend to aggregate one by one. And at some point, it forms a critical size. Here, 6 in the picture. And we are interested in the statistics of this event. Okay, so you can write down what's the statistic of this event. It's the first passage time. The first time, you will form one aggregate of size n, and n is the parameter of your model. So we've done, I think we'll keep a bit the numerical result. We've done a lot of statistics, of numerical results actually about this. Sorry. What we are interested first, like as a modeler, right, is how this time depends on parameters. That's the first thing you want to do. You have an output of your model. You want to say how to understand how it behaves with respect to its parameter. And the key question was for us, what would be the limit of this time when I'm starting with a lot of monomers? Right? What would be the statistic? What would be its variability? What would be its mean? What would be its variance over mean of this when I start with 10 to the 10 or 10 to the 15? And I want to reach, so this is a huge debate, what is N in biology, right? What is the nucleus for the protein amyloid? Maybe in some cases we know now the answer, but at the time I started this job we have no idea. But what you know is that at the end of the experiment, so when the polymers are really stable, right, You can have some rough idea of the measure. So you actually can measure the mass, the physical mass of the polymer, and do some tricks to understand how many monomers it has to get this mass. And they are quite large too, so they at least contain thousands of monomers. They're quite large. So there are two numbers that are large. So at least the size I'm going to reach, and the total mass I'm having in the system. So it's kind of following these kinetics. You have you are going to form very lots of polymers, starting with really a lot of monomers. And the key thing is, how are you going to do to get a variance or a standard deviation with scale of like the mean? So how are you going to do to get still some variability with 10 to the 10 initial number? So here's just a rough idea how you can do this very simple. So here is n equals 7 or 8. So you can still and n equals 3. So you want to reach a 3 there. So here you can still enumerate all the state in your system, right? And you can compute with a backward equation what will be the probability that you start from starting from here. You will go through this state, and at some point you will cross the barrier. You will form 1 3. Okay. So you can do some analytical work on this with this size, with the 10 to the 3 or 10 to the 10 size. I don't know. I'm going to switch to the coarse graining result just to show you that my theorem is true in practice. So what I'm showing here is a first passage term for m going to very large, so up to 10 to the 8. And in the scaling, I'm used to go from the Becker-Doring to the transport equation, which has a name, by the way, it's the Lifshitz-Liozow equation. So what you see here is, for low numbers, so this is like a Gillespie algorithm, and then when I reach a nucleus of size square root of m, I record the time, and each realization is shown here, and the circle dot is the mean. When you see for low numbers, there's still a bunch of variability, but then when you go for high number, all the variability is reduced, central limit theorem-like, which we don't prove, but it looks like this in the simulation, and the CV, the standard deviation over the mean, decrease directly to 0. So we were not really happy. So let me see, use just some video what the dynamics of the system is. Oops. So initially I have all monomers, and here I'm plotting the size distribution of my system. So the size distribution is really this function. Okay, all of the aggregates I have in my system initially is 0. Okay, I start with only monomers. And here you have the monomer variable. Right? So it starts here 3, but it's 3 divided by a scaling factor. Right? So it's a lot. What's epsilon? I think it's 10 minus 3, so 3,000. Not that much, but still. And then I let time to evolve, and I have a transport equation, so you will see swing going in the system. And because the flux of the transport equation is actually nonlinear, it can go right and then a bit left. And what you see, so the blue is, stop at some point. So the blue is really the stochastic model, running the Gillespie algorithm with these kinetics. And the red curve is what you have solving this transport equation with the appropriate boundary condition. So you really need a boundary condition because you're forming aggregate. You start with no aggregate and you're forming aggregate of positive size. So you really need a boundary condition. And then you're forming like a front like this, which looks like a wave. But because the flux is actually depending on C1 and C1 moves through time, this flux is not like a traveling wave, proper traveling wave. It's going right and then left because you lose the monomer.
So why does it go left in the end?
So initially, here, initially, so I'm taking as a coefficient, particular case, but you can use different things. I'm taking p equal 1, and q of x equal, x. So the flux is px c1 minus qx, okay? So this is just c1 minus x. Okay, good. So if x is 0, c1 is 3, so this is positive. But if you reach a size bigger than something, bigger than 3 initially, the flux will be negative. But as you let the time evolve, C1 goes down, okay? And here, C1 is something like 0.5, okay? C1 here is something like 0.5. So then for all size greater than 0.5, roughly here, so it will be 0.8, the flux will be negative. Okay?
There's a lack of monomers is why.
The lack of monomers, definitely. But the monomers they don't go to zero at the end. But so it's a lack of monomer for large aggregate, whereas for small aggregates they still can aggregate. So that's one example. Another one.
Actually, is annealing possible in not just in the model here, but in real biology? Can large filaments combine and
Yeah. So indeed, clearly at the end of the process, these things could happen. The thing is whether it happens at the beginning, it's not so clear. And in our hypothesis, no, it's no. But you can think of it, of course. And for sure, so this annealing, I'm not sure, but for sure the fragmentation of large amyloid, this we know this occurs, but at the end of the process, not at the beginning. Another example is this one. So it's different rate. You get something like this. So here actually the rate is constant. Q is a constant. So it will be like this. So it stays the same sign over all simulations. So maybe it's a bit easier. I should have started with this one. But always go to the right. Up to some point you don't have enough monomers. So if C1 goes to Q, the flux will be 0, and you get something that actually stops to move. Right? It's reach something, and then at this point nothing occurs. Right? It roughly stops to move. So there are some details, and because if the flux is 0, it means that when you go to this limit, you should go to this higher order actually, right? Because the first order is 0, so you should go actually to the second order. So we are at this point to understand exactly what's happening. But here it's the case. And now, actually, the more interesting case for the biology is this one. So when the flux is negative, so here's the initial condition. So I'm starting with now the reverse as before. P equals x, and Q is a constant, 1. So this flux will be x C1 minus 1. Okay? And I have no polymers at the beginning. So I have no polymers at the beginning, and the flux is this. For x equals 0 or small, it's minus 1. Okay? So the flux is going to the left, so nothing happens. So if nothing happens, I still have my monomers. They start at 3, okay? They are roughly 3 for a long time. But if at some point an event occurs, so nothing happens, well, some small oligomers in the stochastic simulation are forming. But if at some point a large polymer is formed, which you will see at some point, yes, then this polymer has reached the critical size for which the flux is positive. Okay, so if x is larger than 1 over C1, is my example, then it has a positive flux and it tends to aggregate everything in the system. So of course, with this simple model, the main drawback is at the end I have a single polymer, which is not the case in the biology, as you mentioned. So
That was not an instantaneous transition, right? Just a short one.
it's a short one. Compared to the time scale of the waiting time, it's very short. But it's not instantaneous indeed. So, yeah, you see it takes like, I don't know if you can see it with the resolution, it's a bit bad. It's continuous, step-by-step process, right? But very fast. And the interesting thing with this is that when you do even with 10 to the 10 monomers, the statistics of the event forming a large polymer is very random. So here, I can't remember what shows the epsilon, but something like 10 to the minus 5. So it's not 10 to the 10 guys because it will be too long in simulation, but it's let's say 10 to the 5. And I have a huge variability between replicates. They all look time shifted. It all depends on when I start. And when I start, it's because it's super fast, they look just time shifted. And if I use the statistics of the CV, at least when epsilon is small enough, so what was my normalization parameter, the standard deviation look like the mean. So it's really like an exponential waiting time, which you could prove which I'm doing right now, trying to prove, using large deviation theory. So it's really like, I have a rare event, and I have to quantify at which rate this rare event can occur. Okay. Yeah, so this leads to the 5 minutes left if you let me explain what is my open problem right now. So we want to quantify this. It's a bit hard for what I figure out, at least for me, to handle large deviation in infinite dimension. Why are we really infinite dimension? Because the limit model looks like a transport equation, right? It's a nonlinear transport equation, so it's dealing with a mass distribution or with a measure distribution. And we want to quantify at which rate some mass will be over a given critical size. Okay, some mass will be over 1 over C1. But the C1 is evolving through time also, so it's not that easy. And there is a much simpler model you can think of. If you impose in your system that a single aggregate is formed, but not as many as the beginning. So if you impose that you have a single place, a single location where you could form a polymer, then the system from infinite dimension goes back to 1 dimension. And you can just try to figure out what is the size of that particular aggregate you impose in your system. And it can go step by step, 1 by 1. And at the limit, so you can put some forward weight and backward weight to go one step further, 1 foot back. You put some weight, and if you do the same kind of scaling, you would converge to a nonlinear differential equation, which exactly look like the characteristic equation actually of the nonlinear transport equation. So it will be an aggregation weight minus a fragmentation weight for the size of this aggregate. Another thing that are much more easier because you are dealing with an ordinary differential equation and not with a PDE. And you can actually do some Friendly-Menzel theories to quantify what will be the rate this guy will switch over a critical barrier. So if, for instance, if P is low at x equals 0, so it's exactly like in this example, you start x equals 0, this is 0, and you have some minus 1. So the limit model, you stay at 0. X equals 0, dx over dt equals minus 1, you stay at 0, or below 0, but you impose some boundary condition at 0. So you stay at 0. But if x is large, then you will cross the threshold and you will start to increase. Okay. So in the stochastic model, you can actually go in both directions with some rate, and in the 1 dimension, okay, you exactly know, you can solve exactly the mean first passage term and the variant, and you can solve everything. And you can prove that doing the same scaling I'm doing here, this converges to the exponential over an integral divided by this epsilon. And this integral is exactly positive when q is bigger than p. Okay, so it's a logarithm of a fraction. And if q is bigger than n times p at least, this logarithm is positive. So then I'm taking the exponential of 1 over epsilon with something positive. So it takes a huge amount of time. So this I can do. Now can I do it with 2 aggregates? It's already a bit harder because you have no exact solution of first passage time. So what I mean by 2 or n clusters, I mean I impose in my system a fixed number of clusters, so 2 to get simple. And this cluster may aggregate or fragmentate with given rate. And the rate of aggregation, they are coupling with each other. So they have a fixed number of monomers they could capture. So the coupling is in the aggregation rate. If one is increasing its size, it will be less likely that the other one increases its size. Okay? And vice versa. So the limit model looks like this. So it can have a flavor of Lotka-Volterra-like equation. So there are a coupling between the 2 guys. Okay? If one is increasing, it will decrease the rate of increase of the other guy. Okay. Whereas in Lotka-Volterra, it will be more in the death rate, I guess. So the phase plane looks like this. So you don't really see, but what's matter actually is at 0, so close to 0, because I'm start at the 0, 0 point. All the flux is towards the boundary, towards the 0 point. So I have to quantify what will be the time I need to switch to some point here. I don't know if you can see, but then the flux is going to the right here, and starting from point 1 is also going to the. So that's really what happened in the numerical simulation. And if I'm doing actually some trajectories of my stochastic discrete process, I will spend a lot of time here, and at some point I will cross the threshold. It was 0.1, I think, and then you go far to the right. And you could have gone exactly in the opposite directions. Anyway, normally, well, it was equally likely that you would have formed an aggregate in this direction. You could have crossed the threshold in this direction. Okay, whether it's this direction. So here is like 10 or 15 trajectories together. So it's even likely to go here, whether to here. But you will never form two clusters. Okay. So now I'm trying to figure out how exactly you can do statistics on this. You can do numerical simulation, you can perform records what's mean first passage time and so on, and it's look very similar as a nonlinear problem. But because it's finite dimension, I have more hope to quantify exactly what is the first passage time. So and the intuition is in the first order, so the exponential 1 over epsilon, the first order you will form a single cluster. You will never form two clusters that will be of macroscopic size. But this remains true. Yes, and I think we'll finish by this. You can also think to many extensions actually in this model. Maybe one that could be interesting is adding diffusion to this model, so taking into account that this monomer actually can move around and encounter an aggregate, and when they are close enough together, they can coagulate. Another question is, and which I always refuse to do, but I think I know how to do it at some point. Can you do data fitting with that number of proteins? So my first thought was, no, you cannot do, and you need a reduced model. So that's why I was going to this limit theorem methodology. But I think now with improving technique of numerical simulation, maybe it could be good. Thanks.
So if you just formally took, even in your simple models, the equations and projected them onto like a chemical launch fund type model, and then just did large deviation theory on that, does that give you good agreement?
Yeah, so it's certainly interesting, like something I figured out talking with someone in Edinburgh, is that it's not the same result. It's roughly the same, if you come back to this, so you had this equation, and the midfield limit is the identity of x equals this, right? So indeed, you could think of this one. Right, I think you are thinking of this one.
Yeah.
Yeah, and indeed it's roughly the same, so with an epsilon here, right? Or the square root epsilon. It's roughly the same picture, but the precise prefactor is different actually. So you don't get this logarithm form. So I think maybe this is something new from some of you, but this equation here, it's not the same when you do the large deviation theory from this model. It's a bit different. I mean, the scaling is the same, so you have exponential of 1 over epsilon. But what you have here, it's actually a bit different.
So how, I forget, how easy is it to get the rate function for these, if you don't go to the chemical algebra, you just start with the master equation?
Well, this is, I have to learn this.
Yeah, this is, yeah.
There's no proper theory for this, to my point of view. So you can do some heuristics.
Where did this logarithm come from then?
Yeah, definitely it's come from
Explicit result.
this product here.
Oh, okay.
You take the logarithm, it becomes a sum,
Oh, I see.
which you can now integrate. And because you took the logarithm, you have to do exponential. So with this logarithm, this is exponential. Comes from this. Which you don't have this, so this logarithm, you don't have it in the.
So you derive that out of the discrete version, basically, not this limiting version.
Yeah, and there was, I mean, because I have a formula,
Yeah,
it
exactly.
was easy for me just to
Yeah.
take the limit, you know, of this formula. But in higher dimension, you don't have this formula, so you need to develop actually a theory for looking like the friendly inverted one.
And you can't use like generating functions or something like that, does that work? No.
To get exact solutions.
Could be a generating
Or,
function
but
is when you have an
you
exact.
can do limiting behavior on generating functions as well, but keep it in the discrete.
You're not talking about doing the large deviation with generating functions, you're just saying trying to work out results.
I'm just saying you have you have something more complete like this sum and then trying to do asymptotics on that. I don't know what the right asymptotics are.
So,
Just randomly saying stuff.
Actually,
Well,
this,
after a long time, eventually it would be really useful, I don't think.
this asymptotics has been obtained in the 80s by Matkowski, Schuss, and Thiers. They did exactly this. They had a random jump process, and actually they didn't go to this. They had to not the Kramer-Moyals approximation. They did the entire sum, use WKB, and this is exactly the solution
Where's the
of
first
the
order of
Hamilton.
WKB?
Yeah, this is the solution of the Hamilton-Jacobi. This is the psi, and you can even get all of the details of the expansions.
Okay.
But the other case, no, I never
Other
seen.
dimension?
No, there is no result on this. This is yeah. This is
So which
interesting.
result are you, who?
Matkowski shows this is the
Third
the published
But you said
5,
somebody
7
else.
papers.
But you said somebody else. Is it in the queuing stuff or is it
No,
something else?
this is in the chemical reaction papers. The published
Okay.
Journal of Chemical Physics. This is
Okay.
Charlie Thiers.
Oh, it's tier, okay,
Yeah.
yeah, that's what you said, tier,
Yeah.
Because I was gonna say maybe the Nessel stuff, which is in
That's,
queuing,
yeah,
might have some of
that's
that
right.
stuff in it.
So some has been published in the queuing theory,
Yeah.
and some went into the chemical reactions papers. So actually, they found out you do the WKB on the master.
equation.
Yeah, that's right. And then you use they have also this jump process which was small, so they have this exactly small parameter, and they found this log is divided by this. But
So
for
what
the other,
ansatz, you try to solve something like putting an ansatz for the
that's right.
Yeah,
something
That-
like this, and then you
Exponential psi.
find the
That's
side.
that's
You
exactly
have an
it.
Hamilton-Jacobi side.
That's right.
But this,
And
from what I figure out, you can only solve the Hamilton-Jacobi if it's one dimension.
yeah. So for
What
the
do
other
you do
case,
if you can't solve it?
so for the other case, we actually, it's very interesting. It turned out to be important for I mean, not this slide, the next slide when you started to have these 2 dimensions. Yeah. So this we had completely coincidence for the production of messenger RNA from a gene. We had also these 2 dimensions because we were interested in having at least 2. We had actually, you can have 2 to 10 messenger RNA, so actually we had something in dimension 10.
Okay.
So we looked at it in dimension 2. It was, we didn't know how to solve it, what is the WKB. So I think this is a tough problem.
So in your system, I guess you have some nonlinear regulation for the one mRNA to.
Yeah, it was more looking, go to the next one. We had exactly this picture where you had the separatrix. No, the one, yes. No, the one before. Yeah, look, you have a separatrix here.
Yeah.
This is, we had exactly this type of picture. We didn't know how to calculate.
Okay.
It's an open question.
So your point is that the discrete jumps greatly complicate the relative to continuous noise.
Yeah, so maybe I could actually go from something like this and see. Have you done this?
but won't you be in trouble because a lot of your stuff is going on?
But that's the thing, I'm afraid of doing this because
Yeah,
most of the gear are 0, so you have to put, if you want really to work with this, you have to put a boundary condition at 0. What will you do if you put a reflexive or something? It will actually matter what you put it at 0.
no, that's what I was thinking, I mean, I don't know if it's in higher dimensions, there's some work with Coombs and one of his postdocs where they were looking at low numbers in T cells and things like that, so where they used generating functions and did some various types of asymptotes.
Usually genetic function works when everything is linear. So
Sorry?
usually it works when all the rates are linear, the generating functions. I mean, I
Yeah.
definitely have a look, but in my
Yeah,
case,
here you have these state
it cannot
dependent.
be linear. So.
Yeah,
But
you have state dependent.
I mean, if you have some nice
Yeah, I
result
know.
in the linear case, I definitely want to.
Yeah, I mean, this other method may work. I mean, there's some higher dimensional stuff in this, using this WKB on discrete stuff, but no lot.
I don't know. I mean,
There's a little bit, but not, but the problem is exactly like you said, as soon as you do that, you end up with these, with coupled, first order wave equation, nonlinear wave equations, and the question is how much can you really get out of it?
Okay, great.